Hello reviewers, this video is used to present my topic Nanoelectromechanical Switches, an approach to low power digital computing. The outline for this video is first NEMS introduction, then its fabrication, NEMS switches, their operation, silicon NEMS switches, silicon carbide NEMS switches, graphene based NEMS switches. These are just the materials to fabricate the NEMS switches. Then we have the challenges and perspectives. Then there is a novel approach, which is the integration of CMOS and NEMS together for the specific applications. Then we'll have conclusion and in the last references. So the term nanoelectromechanical systems or NEMS is used to describe devices integrating electrical and mechanical functionality on the nanoscale. As you can see in the figure also, it's 500 nanometers. NEMS form the next logical miniaturization step from microelectromechanical systems, MEMS. MEMS is integration of sensors, actuators, electronics, photonics, and many other technologies into a meaningful system, enabled by nanometer precision. NEMS fabrication is generally by the materials of silicon dioxide, silicon carbide, and so on. Fabrication methods is like this fabricated using compatible micro machining process, and the three main steps of fabrication are deposition process, lithography, and etching process. NEMS switches. So they are contact based switches. They are composed of a mobile structure that is deflected until it reaches physical contact with an electrode, forming a path for the current to flow. There are two states that can be distinguished. The first state is the zero state, which is also an off state where there is no contact, and the second is the on state where the contact has been formed. As you can see in the picture, the A figure shows the simplified model of a three-terminal switch under electrostatic actuation, and the B represents the cross section of an electrical contact in the on state. So in the off state, the current is limited to vacuum tunneling. Brownian motion displacement currents that appear in the physical gap that separates the mobile structure and the electrode. The low value of the off current, together with its ideally infinitely abrupt transfer response, solve the problem of passive power consumption that traditional CMOS transistors present. The advantages of the NEMS switches are its virtually zero leakage current for negligible static power consumption, the ability to operate with very small voltage signals for low dynamic power consumption, and its robustness against harsh environments such as extreme temperatures. So the operation of the NEMS switches, the key components are a movable structure which can be a single wall or a multi-wall carbon nanotube, and a fixed ground plane which is modeled by a graphite bulk. As you can see in the picture in the figure A also, the position of the tube when the potential is zero. And when the potential is greater than zero, that is when the van der Waals forces and the electrostatic force have been applied, the nanotube is almost forming the contact with the ground. So electrostatic charges are induced when a potential difference is created between the movable structure and the ground plane. The electrostatic charges give rise to electrostatic forces which deflect the movable tube. In addition to electrostatic forces depending on the gap between the movable tube and the ground plane, van der Waals forces also act on the tube and deflect it. Counteracting the electrostatic and van der Waals forces are elastic forces which try to restore the tube to its original straight position. When the applied potential difference between the tube and the ground plane exceeds a certain potential, the tube becomes unstable and collapses onto the ground plane. The potential which causes the tube to collapse onto the ground plane is defined as the pull-in voltage or the collapse voltage. When the pull-in voltage is applied, the tube comes in contact with the ground plane and the device is said to be in the on state. When the potential is released, the tube and the ground plane are separated and the device is said to be in the off state. Here you can see in the figure also the characteristics of the electrostatic NEMS switches. Next is the silicon NEMS switches. They have emerged as an attractive enabling component for new transducers. Ultra-thin silicon nanowires and arrays have been engineered into high-speed vibrating devices, such as very high-frequency resonators and piezoresistive transducers. Then there is a silicon carbide NEMS switches also. It has recently emerged as a material that has enabled some of the best and robust NEMS switches and logic building blocks with abrupt switching, zero leakage, and long lifetime. The device achieve greater than 10 raised to power 7 to 10 raised to power 10 switching cycles recorded without device failure at both room and high temperatures. Examples of low voltage lateral electrostatic NEMS switches enabled by silicon carbide nanowires defined by top-down lithographical processes. This is the example. So there is also a graphene-based NEMS switches, which is currently being in research and developed. These are the electromechanical switch devices employing suspended graphene as movable elements. Their on and off states can be controlled by modulating the electrostatic force applied to the graphene. The devices exhibit on-off ratios of up to 10 raised to power 4 and lifetimes of over 500 cycles. It is a novel approach which is currently being researched for further applications. So this is a figure displaying the graphene-based NEMS switches. So next are the challenges and the perspectives. The structure and architecture of the logic mechanical blocks have to be carefully designed in order to benefit from the low energy of NEM relays while limiting the penalty in the delay of the system. In addition, devices with reliable, reproducible, and stable response are required. Extremely high standards in terms of power, performance, area, and reliability. So first challenge is the reliability at contact. Contact material plays a main role in switch performance. It fixes the minimum operating energy, the active power consumption, which is fixed by the on current value, the cycling endurance of the device. Reliability issues at contact include permanent stiction due to adhesion forces and micro welding, contact wear, tear plastic deformation, environmental effects, humidity or contamination of the contacting surface. High requirements in different domains are needed, which you can see in the table. For the mechanical domain, good contact at low forces, high hardness, scratching, wear and tear resistance. In the electrical domain, we need good conductivity. Chemical domain, stable or chemically inert material. Physical domain, low roughness, and in the thermal domain, high melting point. The next is the energy delay. The intrinsic delay of NEMS switches is at least 3 orders of magnitude bigger than the delay of a single MOS transistor. This delay can be overcome by using NEMS switches in parallel, but their fabrication is very challenging. A new technique, NEMS CMOS co-integration is devised, providing an attractive alternative. So NEMS CMOS co-integration reduces the parasitic capacitance due to interconnections and hence unnecessary delay compared to a system in package solution. But the dimensions and materials are fixed by the CMOS technology. As an alternative, the NEMS devices could be defined on an upper level and connected to the circuitry after the fabrication of the CMOS circuitry. So, in conclusion, the fundamental limitation in the energy efficiency of CMOS digital logic circuits necessitates new logic switch technology to enable continued improvement in chip functionality within power density constraints. NEMS switches are promising candidates for low power applications as they have negligible off-state leakage current and abrupt switching behavior which in principle enables very low switching voltages. Various materials are being used for implementation of NEMS switches. A hybrid approach, CMOS NEMS for very specific functions may seem more easily attained in short term. Here are the references which I used to prepare my video. Thank you so much.